In 5.2, we are still talking about discrete probabilities. We are still talking about step probabilities, okay? Values that are incremental numbers. But in this case, we're looking at a special situation where there's only two steps. There's step one and there's step two. This is called a binomial experiment. So for a binomial experiment, there are only two outcomes, which are called a success and a failure. The variables for those when it comes to probability is the probability of success is P, and the probability of failure is Q. And so we have P and Q. And these are complements, which means if you add them together, you get 100%. There are also a fixed number of trials. So we have to indicate how many trials there are. And each of these trials are independent, which means that the results of one trial do not affect the probability of another trial. They are completely independent trials. And so once you have these four things, these are conditions for a binomial experiment. Perfect examples of this are flipping a coin or polling people to see exactly how many of them have green eyes. Either you have green eyes or you don't have green eyes, or shooting arrows at a target and determining the probability of hitting the target. Either you hit the target or you don't hit the target, right? P and Q, binomial. Okay, so we went through this example here, and we're not going to go through the whole entire thing because we got down to this. And what we're talking about is we're not looking at just the probability of one event happening, of a particular event. We want the probability of all the events happening. We want the distribution of all the events. So if you take a look at this, in this situation, what we had was 3 multiple choice questions, right? So we give you a quiz. There are 3 questions on it. They're multiple choice. There are 4 answers, one of which is correct. And so this is the entire sample space, right? This is the sample space. How many different ways can you get things right? And so if you wanted to know what's the probability of getting none of the problems correct, none of the problems correct, that would be wrong, wrong, wrong. So to get 0 correct, you take the probability of getting them correct to the power of the number that are correct times the probability of getting them incorrect to the power of the number that are incorrect for your event. So if you have 0 correct, that means you get 0 correct and you get 3 incorrect. Or it's P to the 0 power, 0 correct, Q to the 3rd power, because 3 of them would be incorrect. If you want to know what's the probability of getting exactly 1 correct, that would be P to the 1st power for 1 correct, and Q to the 2nd power for 2 incorrect. If you wanted to know about getting 2 correct, again, the pattern is P to the 2nd power, Q to the 1st power. 2 correct, 1 incorrect. Or the probability of getting it correct to the number of correct power, and the probability of getting it incorrect to the number of incorrect. And then finally, 3 incorrect would give you this, 3 and 0, okay? And so we came up with this generic formula, which is this guy, and this guy has 3 components. It has this component, which is the probability of getting something correct to the power of the number of times it's correct, times the probability of getting something incorrect to the power of the number of incorrects. And then we had this guy out here, this NCR, which actually you've seen before. This is from the combination formula, combination pizza, combination permutations. And we talked about the ways to calculate this using Pascal's triangle, right? 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, and so on. And so you take these 3 values. You take your binomial coefficient, you take the probability of success to the power of the success frequency, and you take the probability of failure to the power of the failure frequency, and you multiply them all together. And that is the probability of that event happening. And so you multiply these 3 things together. The tech tool for 5.2, there's nothing you have to do. There's no formulas you have to create. It's all sort of created for you. The green boxes that you see, these green boxes are the inputs. These are the only things you have to put in. So if we're talking about the 3 problems that we just had in this example, there were 3 multiple choice questions. For each question, what's the probability of getting them correct? 0.25. And if we want to know what's the probability of getting exactly 2 correct, so I've got 3 questions. The probability of each one being correct is 1 out of 4. And now I want to know, what is the probability of it getting exactly 2 of those correct? What's the probability of getting 2 of them correct? And so my binomial coefficient, that first number, is a 3. That comes from Pascal's triangle, the combination formula. The success probability, which is the probability of success raised to the power of the number of successes. This would be 0.25 to the second power. That's this number. And then the failure probability is the probability of failure, 0.75, to the power of number of failures, 1, which would be this value. And you take these 3 and you take the product of these values. So you multiply them all together. And you can see this is the formula that I used. I multiplied those 3 numbers together. So the probability, if you have 3 questions, of getting 2 of them correct is about 14%. That's the exact probability of getting exactly 2 correct. What about getting exactly 1 correct? Well, we would change the 2 to a 1. And so the probability of you getting exactly 1 question correct is 42%. What about getting them all wrong? What's the probability of getting them all wrong? None of them correct. 42%. What's the probability of getting them all right? Not very good. It looks like 1.5, 1.6%. So if you have 3 multiple choice questions, each with 4 answers, one of which is correct for a probability of 0.25 success, you have a 1.5% chance of guessing randomly those 3 questions and getting all 3 correct. You have a 1.5% chance of acing that test just on random guessing. Remember when we did standard deviation way back a while ago, and we had you build this great big elaborate spreadsheet where you found the mean, and then you found the difference from the mean, and then you found the square of the difference from the mean, and then you found the sum of the squares of the difference from the mean? Remember how you build all that? And then we showed you, oh, you could actually do all of that with this one simple formula in Google Sheets. Same thing happens here. Here is that one simple formula. The formula that does all of this automatically for you in one shot is binom dist. You gotta love the people that come up with the names of these formulas. Binomial distribution, that's what this is. So if you use the formula binom dist, here are the inputs. You have to put in R. So what is R? R is the number that we want correct, the number that are successful, okay? The next number is N, which is the total number. And then P is the probability of success. Again, the same 3 inputs we used earlier. Once you put in those 3 inputs, the next and final variable is, do you want this to be cumulative or not? To be cumulative, if we want an exact number, 2 and only 2 correct, then we have to say false for the cumulative. We don't want it to add them all up. But if we say true to the cumulative, then what this formula does is it finds the probability of getting 2 correct, 1 correct, and none correct. It accumulates all of the probabilities up to and including 2 correct. So it adds them together. So in these 2 situations, row 12 and row 13, row 12 will tell you what's the probability of getting exactly 2 correct, exactly 2. Row 13 will tell you the probability of getting at most 2 correct, which means none correct, 1 correct, and 2 correct. Given this information, we know that there's going to be 7 at-bats, so N is 7. We want 2 of them to be successful, 2 hits, and the player's batting average is 0.315. And so if you wanted to, you could say, okay, here's the binomial probability coefficient. Here's the probability of success to the power of number of successes. Here's the probability of failure to the power of number of failures. And if you multiply those all together, you get this. Or you could put it all into a single formula and get this value. So what is the probability? These two numbers should match. One was built, it was constructed by multiplying these three things together. The other one was using the Google formula binom dist. So either one will work. We're going to copy this and we're going to paste it in there. And so what's the probability that he gets exactly 2 hits at the next 7 at bats? 0.314. That's the probability of getting exactly 2 hits. Now, our tech tool gives us an additional piece of information. This right here, the 0.61, would be the cumulative total. So what's the probability that he gets no hits, 1 hit, or 2 hits, right? It adds up the cumulatives up to and including 2 hits. So that probability would be 61%. So there's a 61% that this batter would get no hit, 1 hit, or 2 hits on his next 7 at bats. It accumulates up to the value in question, which would be 2 hits out of 7. So we're looking at this and we're saying, okay, you've got a binomial distribution. There you go, with 15 items. Okay, so n is 15. The probability of success is 0.3. So we can put that in 0.3. There we go. What is the probability of getting exactly 6 correct? That's what this means, all these columns. The probability of getting exactly 6 correct. So I need to say 6 out of 15, right? That's my probability. I've got 15 options. I want to know the probability of getting exactly 6. And each probability is, the probability of success is 0.3. So here's my binomial coefficient. Here's my probability of success to a power. Here's my probability of failure to a power. And if I multiply these 3 together, I get this number. Or if I want to use the binomial distribution formula from Google Sheets, I get the same number. So this is the value of getting exactly 6. Exactly 6. Okay. Now let's look at the next ones. What's the probability of getting less than or equal to 6? Less than or equal to 6. So this would be getting a 0, a 1, a 2, a 3, a 4, a 5, or a 6. What is that probability? What is the cumulative probability? Oh, that's this number right here. Cumulative probability, right? So we'll copy and paste that there. Again, you have to understand what the tech tool is telling you, what it's calculating, what these mean. It's not going to tell you, go to cell C13 and copy and paste that number. You have to figure that out. You have to understand what less than or equal to 6 means, okay? And what these values are telling you. Well, I try to help you out by telling you exact probability and cumulative probability. You got to know what those words mean. You got to know what cumulative means. It means add them all up from 0. So now look at the next one. And this is where you have to use some of the gray matter upstairs, right? What about less than 6? Not less than or equal to, but less than 6. So if I know this is the value, this is the probability of less than or equal to 6, and this is the probability exactly at 6, you subtract these two numbers, right? That'll give you the probability of less than 6. So if I take this number and I subtract this number, that will give me the probability that is less than 6. Not less than or equal to, but less than. But I'm going to leave it like this, so that way you can see the mathematics, right? Like, I want you to understand where that number comes from. Okay, what about greater than 6? And here's where you have to use the idea of a complement, right? And so if this value is less than or equal to 6, then the values greater than 6 have to be 1 minus that value. So we'll put that right there. And then finally, what is the value greater than or equal to 6? Well, it's going to be the equal to 6 plus the greater than 6. This is getting quite a lot of stuff to type in. But I'm showing you the calculations, right? These aren't things, these values you can't just plug into the spreadsheet and get the answer for all 5 of these. You have to be able to logically reason and say, okay, this is asking for less than, this is asking for less than or equal to, this is greater than, this is greater than or equal to. So if you do find these numerical values, just to show you that we got them all right, there you go. Just like we did with real data, we wanted to find the mean and the standard deviation, right? And we showed you how to do the mean and standard deviation previously with discrete probability distributions, right? And this time we're talking about the mean and standard deviation of a special type of discrete probability distribution, the binomial distribution, okay? So remember, 5.2 and 5.3 are all about the binomial distribution. So in general, for discrete probabilities, you may remember this from 5.1. This is how we calculated the mean. You took the value, you multiplied it by the probability, and then you added these up. Remember we did that like in the spreadsheet? To find the variance, you took the mean, you found the difference from the mean, then you squared the difference from the mean, and then you multiplied by the probability. And then after you did all that, you added them all up. To find the standard deviation, you square rooted the variance, right? But we had entire spreadsheets doing these things. That is for a generic discrete probability. Discrete probability. In 5.3, we are talking about binomial probabilities, discrete binomial probabilities. So what we need to do is figure out how to calculate the mean and the standard deviation for discrete binomial probability distributions. Binomial, 2 options, right? P and Q. And here's how you do it. So to find the mean, you simply take N and multiply it by P, and you're done. So remember, N is the number of trials, and P is the probability of success. You take the number of trials, you multiply it by the probability of success, and that is your average for a binomial probability distribution. This only works for a binomial probability distribution. Yes or no? Okay, P or Q, success or failure. To find the variance, again, it's so easy. You take N, you multiply it by P, and you multiply it by Q, and that's it. So again, you take the number of trials, you multiply it by the probability of success, and you multiply that by the probability of failure. N times P times Q, and you're done. To find the standard deviation, you just square root that NPQ. And so you may have noticed, if we go back to the tech tool for 5.2, underneath where we put in our inputs, underneath where we calculated the 3 individual items, underneath where we multiplied those all together to get the product, underneath where we put in our values here and here for the formula, here are the mean, the variance, and the standard deviation of the data set. So here's N times P, here's N times P times Q, and here is N times P times Q, square root. So in an election, 49% of the people voted to re-elect the incumbent. This is a binomial situation because you either voted yay or you voted nay, right? Binomial. A sample of 772 random people are selected. What are the number of trials? Well, that's pretty easy. That's 7,720. There you go. What is the probability of voting yes for the incumbent? So we'll say that's going to be 0.49, right? That would be the probability as a decimal. What is the average? So N times P. So you could do this on a calculator, or you could come over here and you could put in 7,720 people in the trial, and the probability of success is 0.49. Whoops, 0.49. And I don't even need to put in an R value. If I come down here, there is the mean. So I copy that number and I put it in here. And then what is the standard deviation of the sample who voted yay? Here is the standard deviation. Construct a binomial probability distribution table using n equals 5 and p equals 0.29. So what x values can we have? If there's 5 things, we can have 0, 1, 2, 3, 4, and 5, right? And so what's the probability of getting exactly 0 correct? All right, let's go here. I've got 5 items, so n is 5. R is 0, so there's 0. And the probability of success is 0.29. There you go. So the probability of getting exactly 0 correct would be this number here, or this number here. Either one, they're the same number. So copy, paste. What's the probability of getting exactly 1 correct? I'll change that to a 1. And now I get this. And getting 2 correct. There we go. There's the number 2. Copy, paste. Probability of getting 3 correct. You can see where this is going. So here are all the probabilities. If you added these all up, what would you get? 1, right? If you added all those probabilities up, you would get 1. But this is the probability distribution, the distribution of the probabilities for all the events, okay? What would the average be? 1.45. On average, you would expect to get 1.45. Look at that. Look at how high these averages are here and here, right? There's a lot of 1s and a lot of 2s. There's not a lot of 5s. There's not a lot of 4s. There are a lot of 1s and 2s. And so the average overall is going to be about 1.45, and your standard deviation is going to be that number right there. So again, make sure you know how to use the tech tool. It is a tool, right? And like all tools, if you don't know how to use them appropriately, you can get problems wrong, right? If you don't know how to use a hammer correctly, you can cause great damage. It's a tool like a hammer. Use it correctly, and use it efficiently to help you learn statistics, right? Just like you use a hammer to help you build a house, maybe a birdhouse. You can also use a spreadsheet as a tool to help you learn statistics.